What if Pluto was never supposed to exist? For decades, Pluto was treated as an afterthought. Too small to matter. Too far away to study. Too cold to change. It was dismissed as a leftover, a relic from the early solar system, frozen in time and stripped of significance. Even when it was discovered, Pluto never truly belonged. And when it was finally removed from the list of planets, many assumed the story was over. But in 2015, something extraordinary happened. After a 9-year journey through deep space, a small spacecraft passed silently by Pluto. It did not stay. It did not slow down. It merely looked, and what it saw overturned everything we thought we knew. Beneath the ice was movement. Across the surface were mountains, flowing plains, and signs of renewal. Above it all, a fragile atmosphere still breathed. This is not the story of a demoted planet seeking redemption. It is the story of a silent world that refused to conform to our expectations. And once we truly see Pluto, the question is no longer why it isn't a planet, but how a world like this was ever able to exist at all. That misunderstanding did not begin with data from a passing spacecraft. It began in the long years when Pluto was little more than a rumor with coordinates. For most of the 20th century, Pluto existed as a smudge, a faint disturbance on photographic plates, a point that moved when the background stars did not. When Clyde Tombaugh found it in the early part of the 20th century, in the year 1930, the discovery added a new object to the charts, but not yet a new world to the imagination. The telescopes of that era could not sharpen Pluto into anything more than a changing dot. Its brightness shifted with rotation. Its position slid slowly against the sky. That motion was enough to prove it was real, but not enough to show what it was. Distance made it remote. Size made it obscure. Together, they downgraded it to an abstraction. Even later, when the Hubble Space Telescope turned toward Pluto, the transformation was incomplete. Hubble could finally resolve something more than a single, featureless point. Over several observing campaigns in the early years of the 21st century, astronomers stitched together blurred maps that showed bright and dark regions, a mottled surface, hints of patterns that could be continents or coincidence. But even those images were deceptive in their own way. They suggested that Pluto had been seen, when in truth only its outline had. No mountains, no plains, no fractures, just changing patches of light. It was like judging a book by the thickness of its spine. Meanwhile, physical reality did not care. Pluto continued to orbit the Sun at an average distance of about 39 astronomical units, roughly 3.7 billion miles from the star that warms it. That distance placed it so far beyond ordinary experience that numbers themselves began to lose meaning. Light from the Sun, which reaches Earth in about 8 minutes, takes several hours to arrive there. Human language struggles to picture that delay without quietly turning it into metaphor. From such a distance, almost everything about Pluto had to be inferred. Its mass was estimated from the motion of its largest moon. Its size was constrained by how much light it reflected and how it blocked starlight during rare alignments. Its composition was modeled rather than seen, using spectra taken through Earth's turbulent atmosphere. Each new calculation narrowed the possible answers. None of them required Pluto to be interesting. So a story took shape. Small, cold, distant, a leftover from formation, a frozen relic. The adjectives hardened around Pluto long before any evidence could challenge them. In catalogues and diagrams, it migrated toward the margins. Not quite one of the main planets, not quite empty space. A footnote that kept its orbit. Inside the scientific community, priorities followed the story. Missions proposed to visit Pluto were written, debated, and quietly cancelled. Time on large telescopes was allocated to objects thought to be more revealing. Mars promised ancient water. Jupiter and Saturn promised complex atmospheres and swirling storms. Pluto promised what? Exactly. A frozen ball of ice and rock at the edge of the system did not seem urgent. There is a quiet pattern in that. When something is far away, small, and difficult to resolve, we often decide in advance that nothing important can be happening there. The unknown is not just distant. It is downgraded. It is treated as a safe emptiness in which our assumptions can sit unchallenged. Hubble's blurred maps of Pluto reinforced this complacency. The data were impressive by any engineering standard, yet the results still looked like a world out of focus. A handful of bright areas, some darker bands, variations that could be explained as simple differences in frost and rock, perhaps shaped in the distant past and then locked into permanence. If you already believed Pluto was geologically dead, the images politely agreed with you. They did not show craters, but they did not show their absence either. They did not show mountains, but they did not forbid them. They simply left room for the simplest story. And the simplest story won. Over time, these assumptions took on the weight of fact. Textbooks describe Pluto as a small icy body, a relic of planet formation, an object that had not changed much since the early history of the solar system. The uncertainties were sometimes mentioned in fine print, but the tone remained confident. The world was too small to generate much internal heat, too far from the sun to drive vigorous weather, too remote to be anything other than a preserved fragment of the past. From a human perspective, this confidence was understandable. The solar system seemed organized, large planets near and far, smaller bodies in belts and clouds, a clear gradient of energy and activity. Closer to the sun, complexity. Farther away, simplicity. Somewhere beyond Neptune, the pattern was expected to fade into quiet debris. Pluto's orbit, long and stretched, fed that picture. It takes roughly 248 Earth years to complete a single journey around the Sun. No one alive will see it return to the same place it held when Tombaugh first photographed it. Over such timescales, change feels hypothetical. If a landscape shifts over millions of years, and no one is there to watch, it becomes easy to call it static. Yet, the absence of witnesses does not guarantee the absence of events. A world does not need our attention to remain active. Plates can move, ice can flow, atmospheres can rise and fall on cycles far beyond a human lifespan. Geological time, by its nature, does not wait for us to be ready. Still, most working models treated Pluto as if time had largely stopped there. Any internal heat left over from its formation was assumed to have leaked away long ago. Radioactive elements in its interior were thought too scarce to sustain vigorous activity. Without an ongoing energy source, there seemed to be no way to erase craters, rearrange the surface, or sustain an atmosphere for long. The logic was clean, elegant, comfortable. At the outer edge of the planetary system, entropy would have had more than enough time to finish its work. What remained would be a frozen archive, not an evolving world. This way of thinking did more than describe Pluto. It placed a boundary on where complexity was allowed to occur. We could imagine volcanoes on Earth, ice geysers on a moon of Saturn, a thick atmosphere on Titan. But in the Kuiper Belt, beyond the main planetary family, we pictured mostly rubble and frost. Worlds there were granted existence, but not depth. For decades, Pluto lived inside that mental boundary. It was cited in lectures, drawn in diagrams, and used as an example of a class of small icy bodies. It existed as a useful placeholder in theories of how the solar system formed. It helped balance equations. It helped tidy models. It did not disturb them. In that sense, Pluto, before it was truly seen, was less an object than a projection. We saw in it what we expected to find at the edge of the system, something small, cold, simple, and finished. The lack of detail allowed that expectation to harden unchecked. And so, by the time New Horizons was launched, Pluto was already surrounded by decades of certainty built on partial information. Instruments on Earth and in orbit had measured its orbit, its approximate size, its average reflectivity, its distance, its slow path through the dark. Those numbers were real, but between them lay an entire world we had quietly decided not to imagine. The tragedy is not that we knew too little. It is that we mistook that little for enough. Once that small set of facts hardened into a picture, curiosity slowed down long before the questions did. The assumptions that followed were not careless. They were built from real physics, then stretched quietly past the point where evidence could still support them. At the center of those assumptions was a simple idea. Worlds have to earn their complexity. They need size. They need heat. They need a steady supply of energy over time. Pluto, by every early estimate, had almost none of this. Its mass, inferred from the dance with its moon, is only a tiny fraction of Earth's. Pluto carries roughly 1/500th the mass of our planet, a small reservoir of rock and ice trying to hold on to warmth in deep space. Its mean radius is about 1,188 kilometers, barely enough to qualify as large on planetary scales. Closer in size to some moons than to the worlds we usually place on diagrams. Small bodies cool quickly. That was the rule. The logic is straightforward. When a world forms, the energy of countless collisions and compressions is trapped as heat. Over time, that heat leaks away into space. The smaller the object, the faster the heat escapes. Given billions of years, a body of Pluto's size should see its interior temperature drop toward equilibrium with the frozen vacuum around it. What begins as molten rock and slush should end as solid, unmoving stone and ice. There is another source of heat, the slow decay of radioactive elements in rock. On Earth, that decay helps keep the mantle convecting and the crust shifting. But Pluto, with its modest mass and mixture of rock and volatile ices, was expected to contain far less radioactive material, less fuel, less heat, less time before everything inside cooled and locked. From that reasoning came a quiet conclusion. Whatever processes once shaped Pluto's surface must have happened early, perhaps in the first few 100 million years after formation, when impacts were common and energy was abundant. After that, the story should have ended. No more large flows of ice. No more rising plumes. No more slow flexing of the crust, only craters accumulating, one after another, recording impacts over more than 4 billion years of exposure. Temperature estimates reinforced this picture. Calculations placed Pluto's surface in a range between about 40 and 60 Kelvin, a span just a little above the temperature of interstellar space. At such low temperatures, nitrogen becomes ice, methane freezes solid, and water behaves more like rock than like anything fluid. In that regime, ordinary intuition fails. A landscape can be composed of substances we think of as gas, yet behave as hard pavement. To many, that sounded like a recipe for stillness. Distance deepened the assumption. Pluto orbits the Sun on an elongated path, spending much of its long year far beyond the orbit of Neptune. Averaged over time, it receives less than 1,000th of the sunlight that reaches Earth. That trickle of energy seemed too weak to drive an active atmosphere, let alone cycles of condensation, sublimation, and weather. If anything moved on Pluto, it was expected to do so slowly, and long ago. Models of small, icy bodies followed a similar script. For moons smaller than Pluto, like many of those beyond Saturn, the expectation was that only those with strong tidal forces from a giant planet could stay geologically active. The classic example was a moon like Io, heated by the relentless push and pull of Jupiter's gravity. By contrast, Pluto travels mostly alone. Its large moon, Charon, is locked in a stable dance. But the tidal squeezing between them is mild compared to the violent flexing inside Io. Even Charon's existence, discovered in the late 1970s, seemed to confirm the idea of a frozen system. Here was a companion roughly half the diameter of Pluto, about 1,200 kilometers across, tidally locked so that the same faces always stared at each other. Two bodies rotating in step. 2 worlds long, settled into mutual balance. It felt like the cosmic image of a system that had finished its negotiations with time. When planetary scientists looked at this arrangement, they read it through the lens of thermodynamics and gravity. A small mass, a thin trickle of sunlight, modest tidal forces, a surface temperature deep in the cryogenic range. Every term pushed toward the same conclusion: inactivity. The details varied from paper to paper, but the underlying narrative barely shifted. The expected surface, then, was one of saturation, an old crust, layered with craters of all sizes, overlapping, scar upon scar. At small scales, maybe some patterns of frost. At larger scales, perhaps the outlines of ancient basins or ridges. But everything would be ancient. Everything would be preserved. Pluto was assumed to be a time capsule, not a laboratory. Behind this was a deeper habit of thought. In science, it is natural to search for thresholds. Above a certain mass, an atmosphere can cling to a planet. Below a certain mass, it escapes into space. Above a certain size, internal heat can hang on for eons. Below it, the core freezes. Thresholds give us rules. Rules give us categories. Categories give us the comfort of knowing where things belong. For Pluto, the threshold seemed uncompromising. Its escape velocity, determined by its modest mass and radius, is only a little over 1 kilometer per second. That is far below the speed of molecules in a warm gas. So any atmosphere it has must be cold and thin, easily stripped or frozen out as it moves along its orbit. Any internal ocean would be difficult to preserve under a shell that wants to conduct heat away into space. Add to this its age. Pluto has existed for, on the order of 4.5 billion years, born in the same early chaos that formed the other major bodies. Over such a time span, even small differences accumulate. A world slightly too small, slightly too poor in heat sources, slightly too exposed to the cold, should see any original complexity eroded into simplification. The assumptions were not reckless. They were careful extrapolations from physics that works very well elsewhere. They came from the same equations that successfully describe Earth's cooling interior. The volcanic histories of Mars and Venus, the icy shells of Jovian moons, the ring systems of outer planets. In each of those cases, mass and distance and composition feed into predictions that match what we see. So when those equations were pointed at Pluto, the resulting picture felt trustworthy. On a graph plotting planetary size against geological activity, Pluto fell near the quiet end. On a diagram of solar energy against atmospheric pressure, it occupied a corner dominated by frost and near vacuum. Complexity, if it had ever risen there, was expected to have sunk back into stillness. This is where something subtle happens. Over time, these models stop being treated as possibilities and start being treated as portraits. What began as Pluto should probably look like this gradually becomes Pluto looks like this. The conditional evaporates. The boundary between prediction and description blurs. In everyday life, we do something similar. We meet a few people from far away and quietly decide we understand the many. We see a single street and think we know the city. We hear one story about a place and let it stand in for all the others that were never told. The further something is from us, the more easily our pictures of it turn into certainty. For Pluto, The scientific version of this tendency meant that untested assumptions grew heavier with each passing decade. Proposals for missions had to fight not only budgets, but also the feeling that there was nothing fundamentally new to learn. Why spend the effort to visit a place whose story had already been sketched in equations and confirmed, it seemed, by blurred images? In that silence, the word dead began to attach itself. A dead world. A fossil. An icy remnant. The language was not meant to be poetic, it was meant to be efficient. But it carried weight. It suggested that time had done all it could do there, and then stopped. A kind of cosmic full stop. Underneath, though, the universe was under no obligation to respect these limits. Heat does not check our planet lists before moving. Ice does not read our diagrams before flowing. A small world does not ask permission before refusing to match the categories built for larger ones. If there is an unease buried in Pluto's story, it begins here. In the quiet fact that careful reasoning, applied honestly, can still lead us to a place that reality simply does not occupy. Not because the reasoning is flawed, but because the system we are trying to describe is more intricate than our chosen parameters admit. We like to think that with enough data points, enough patterns, enough well-tested rules, the universe will gradually surrender its surprises. Pluto sits in the opposite direction. Using the same rules that work almost everywhere else, we wrote it into the role of a minor, finished object, a cold stone at the edge of the map. And yet, when New Horizons finally approached, that script began to fail, line by line. The assumptions that said Pluto should not exist as an active world were not erased in an instant. They remained mathematically sound, individually reasonable. What changed was the realization that they had been woven together into something larger than they were ever meant to be. A story about where complexity is allowed to live. In that light, Pluto becomes more than a distant sphere of ice and rock. It becomes a quiet test of how far we are willing to trust our categories, and how quickly we declare reality settled when it is merely unseen. One of the clearest examples of how our stories harden into certainty was written directly into the sky. We could shape detailed portraits of entire galaxies. Yet the small world, hiding at the edge of our own system, stayed unresolved, as if the universe were quietly choosing where we were allowed to look. From Earth, the Andromeda galaxy sprawls across the night like a faint, elongated cloud. It is the nearest large spiral galaxy beyond the Milky Way, sitting at a distance of about 2.5 million light-years. On a truly dark night, with patient eyes, it is visible without any instrument at all. Our telescopes have learned to dissect it into clusters, dust lanes, star-forming regions, even to measure the motion of its stars around a massive center. In terms of apparent size, Andromeda is immense. On the sky, it stretches roughly a few degrees, about 2.8 degrees across in detailed images, making it several times wider than the full moon. That breadth is what allows us to see structure. Each point in the galaxy is too far and too faint on its own, but together they fill enough of the sky that our instruments can spread them out, resolve them, turn distance into a map. Pluto never had that advantage. It is close by comparison, a member of our own planetary family. But its physical size is tiny, and its distance, though much smaller than that of a galaxy, is still enormous on human scales. The combination makes its apparent disk on the sky extremely small. As seen from Earth, Pluto's angular diameter is measured at only a little under 1/10 of an arcsecond, a sliver so narrow that it lies near the limits of what even space telescopes can distinguish from a point. Most of the time, then, Pluto did not look like a world. It looked like a star that moved. Its total brightness could be measured. Its color could be approximated. Its changing position could be tracked with precision. But the light itself refused to spread into an image. All of Pluto's geography, all of its history, collapsed into a single unresolved dot. The Hubble Space Telescope was built precisely to fight this kind of blur. Its primary mirror, carefully polished and placed above the atmosphere, is about 2.4 meters across. That diameter sets the scale for how finely it can slice the sky into detail. For large, extended objects like galaxies and nebulae, Hubble's vision is transformative. Swirling arms, filaments of gas, sharp knots of star formation. For something as small as Pluto, Hubble operates at the edge of its resolving power, extracting only a handful of pixels that suggest bright and dark regions, but no crisp contours. This contrast can feel backwards. Our instruments can reveal structure in objects millions of light-years away, yet they struggle with a body orbiting inside our own celestial neighborhood. The reason is not distance alone, but geometry. What matters is not how far something is, but how much of the sky it occupies. A vast galaxy can be unimaginably distant and still sprawl across a noticeable patch. A small world can be comparatively near and remain visually microscopic. Earth's atmosphere makes this worse. Turbulent layers of air blur incoming starlight, smearing it into blobs that are larger than the true angular size of many objects. This seeing effect means that from the ground, even with very large telescopes, Pluto looks almost identical to the stars around it, a flickering point, sharp only in position, not in form. When all detail is compressed into a point, imagination rushes in to fill the gap. The irony is that we often treat whatever we can image sharply as more real than what remains unresolved. Galaxies, with their spiral arms and glowing cores, feel concrete. We have photographs, posters, desktop wallpapers. We can point to individual regions and give them names. Pluto, for most of its observed history, had none of that. It lived as data tables, orbital diagrams, and artist impressions. Its presence in our mental universe was largely statistical, yet the photons were always there, arriving patiently from the edge of the system. Every night that Pluto rose, light reflected from its surface carried information about craters, plains, and ice. But our telescopes could not separate those signals from one another. All of that complexity arrived stacked on a single pixel, folded into a value we labeled simply as brightness. There is something quietly unsettling in that. Reality can be detailed and active, yet appear flat and simple when our instruments are not tuned to the right scale. The world is not required to look as complex as it is. It reveals only as much structure as our tools and attention allow. The story of galaxies and Pluto makes that clear. When we look at Andromeda through Hubble, we are not seeing it as it truly is, but as it appears under the specific constraints of our optics. Its bright spiral pattern is the product of enormous scale and distance working with the telescope's resolution. When we try to look at Pluto with the same instrument, the laws of optics answer with a limit. Below a certain size on the sky, everything looks the same. Our confidence, however, often ignores such limits. We speak about the universe as if access were uniform, as if every object could be known to the same depth given enough curiosity. In practice, our knowledge is shaped by a strange mix of what is large enough to resolve, bright enough to detect, and important enough to fund. We are not exploring the universe evenly. We are tracing islands of detail in a sea of tolerated ignorance. Pluto fell outside those favored islands for a long time. It did not broadcast radio waves like pulsars. It did not explode like supernovae. It did not host the kind of dramatic, high-energy phenomena that draw telescopes toward them. It was quiet, dim, hard to resolve. Everything about it encouraged the belief that it could be safely simplified. In that sense, the contrast with galaxies is not just optical, it is psychological. We are drawn to the spectacular and the distant. the things that enlarge our sense of scale. A galaxy offers that immediately. Billions of stars, vast arms of gas and dust, a luminous center likely wrapped around a black hole. Pluto, in the shorthand of funding proposals and public interest, offered almost nothing. A tiny icy body, one among many, almost indistinguishable from its peers. But the universe is under no obligation to align drama with visibility. There is no rule that says the most interesting processes must occur where our diagrams already look impressive. It is entirely possible, and Pluto is evidence of this, for a world to hide its complexity not behind distance, but behind angular size and assumptions. Think of how often we mistake clarity of image for completeness of understanding. A high-resolution photograph of a galaxy can create the illusion that we finally see it as it is, when in reality we are still blind to most of its mass, most of its history, most of the interactions shaping it. In the same way, a blurred point like Pluto can trick us into believing there is less to know, when in fact almost everything is still unknown. The reasons we could see galaxies but not Pluto, then, are technical and simple: optics, resolution, angular size, atmospheric distortion, instrument design. But the consequences of that imbalance extend further. They shaped what we chose to consider worthy of attention. They shaped which worlds we believed deserved narratives, and which were left as labels on charts. For a long time, Pluto's punishment for being small and hard to image was to be treated as simple. Its entire surface, its internal structure, its possible ocean, its layered atmosphere, all compressed into a single assumption: nothing much is happening there. The universe did not tell us this. Our instruments did, and we listened as if they were describing the world, rather than their own limits. That is perhaps the quiet lesson hidden inside this optical problem. We are always looking through something: a mirror, a lens, an atmosphere, a theory, a budget, a preference. Whatever we call clear vision is really just the latest state of our filters. Galaxies pass through those filters and emerge as sharp, detailed symbols of cosmic grandeur. Pluto passed through and emerged as a blur, only when a small spacecraft rushed past it, ignoring the old hierarchy of what was worth seeing. Did that blur finally sharpen into a world? And in that moment, the fact that we could once resolve entire galaxies, while Pluto remained a rumor, became less a technical footnote, and more a quiet indictment of how easily we confuse what we can see with all that there is. The decision to send that small spacecraft was not inevitable. It was the result of a long argument with indifference, fought mostly on paper, long before any metal left the ground. For years, Pluto had missions that existed only as proposals and cancellations. In the early 1990s, engineers and scientists sketched out concepts called Pluto Fast Flyby and Pluto Kuiper Express. Lean spacecraft meant to rush past the distant world before its atmosphere froze out onto the surface. They were redesigned, renamed, and slowly strangled by rising cost estimates. In the year 2000, Pluto Kuiper Express was formally stopped, its projected budget climbing toward roughly $500 million. Its launch date slipping further from reality. At that point, it was entirely plausible that no mission to Pluto would fly in the lifetime of anyone then working on it. The outer planets had already been visited by other probes. The urgency seemed low. There were many ways for the story to end quietly in a meeting room, with a line through a line item and a different priority chosen instead. New horizons emerged from that near absence as a kind of last attempt. A group of scientists who refused to let the idea die rebuilt the mission to fit within a new program, with stricter limits and a narrower focus. Their design was simple in intent: a small spacecraft, minimal but capable, thrown as fast as possible toward a target that most of the world had already filed under unnecessary. In 9 sums, NASA formally approved New Horizons in the year 2001, under a program called New Frontiers, dedicated to medium-class planetary missions. Approval did not guarantee safety. In subsequent years, the mission's funding was questioned, trimmed, threatened. At one point, political pressure nearly removed it from the budget altogether, and outside advocates had to argue not for glory, but for the simple principle that the last unexplored major world deserved at least one close look. By the time the spacecraft was ready, Pluto's own status had become unstable. When design work began, Pluto was still officially counted as the 9th planet, while New Horizons was en route. The definition changed, and Pluto was reclassified as a dwarf planet. The mission did not change trajectory. The spacecraft did not turn around. A world's label shifted. Its orbit did not. On a cold day in mid-January of the year 2006, New Horizons finally left Earth. It rode an Atlas launch vehicle and a solid fuel upper stage that pushed it harder than any previous planetary probe. At separation, it was moving at about 36,000 miles per hour, roughly 58,000 kilometers per hour relative to Earth, the fastest departure speed any spacecraft had achieved up to that time. That velocity was not extravagance. It was necessity. The window to reach Pluto before its atmosphere collapsed back onto the surface was closing. Even with that speed, a direct flight would have taken well over a decade. So the trajectory was bent to pass near Jupiter, using the giant planet's gravity as an extra engine. In late February of the year 2007, a little over 1 year after launch, New Horizons skimmed past Jupiter at a distance of about 1.4 million miles, letting the planet's motion sling it into a steeper solar orbit. That encounter shaved on the order of 3 to 5 years off the travel time to Pluto, reducing a journey that might have taken 14 years to something under 10. After Jupiter, there was no more help. The spacecraft entered a long, dim stretch of space where sunlight weakened and the geometry of the mission became simple. Keep going, and do not fail. Most of those years were spent in electronic hibernation. New Horizons would wake for brief checkouts, then return to a low-power state to preserve its systems. It coasted in a darkness where no one was watching continuously. Yet every movement was still being tracked from a deep space network of antennas on Earth. The cruise phase was, in human terms, empty. No dramatic images, no regular news, just a faint radio tone crossing a gulf that widened day by day. By the time the spacecraft neared Pluto, it had traveled more than 3 billion miles, on the order of 4.8 billion kilometers. Since launch, each status signal took several hours to make the trip back to Earth, and every course correction had to be calculated with the knowledge that any mistake would simply continue, uncorrected, into the void. From launch in the year 2006 to the flyby in mid-July of the year 2015, about 9.5 years passed. For the spacecraft, this was a single continuous arc. For the people involved, it was almost a career. Students who joined the team at the beginning finished degrees, had children, changed roles, and still, the probe had not yet reached its main target. The mission existed at a timescale where human lives and institutional attention span began to drift apart. That temporal mismatch is part of why New Horizons almost did not happen. Human institutions are built around elections, budget cycles, and shifting priorities measured in months and years. A mission to Pluto requires patience, measured in decades. To support something like that, generation boundaries have to loosen. People must commit to goals whose culmination they might watch only at the end of their working lives, or not at all. There is a quiet tension here. The universe offers processes that unfold over vast spans of time, Our species builds systems that struggle to think beyond the next funding review. New Horizons sits precisely in that gap. Its survival depended on repeated decisions by different groups of people to keep honoring a promise made years earlier to visit a small, distant world that most would never see with their own eyes. Technically, the spacecraft itself reflects this narrow margin. It was built light, because mass is expensive in rocket performance. Its instruments were chosen for efficiency, each one serving multiple scientific roles. Its power comes from a single radioisotope generator, producing only a few hundred watts, comparable to a household light bulb. There was no extra capacity for indulgence, no room for heavy backup systems. The design philosophy was closer to a single shot than a fully redundant observatory. The mission plan was equally unforgiving. New Horizons would not enter orbit around Pluto. That would have required propellant it did not have, and a slower trajectory that would have missed the narrow atmospheric window. Instead, it would perform a flyby, hurtling past the system at tens of thousands of miles per hour, gathering as much data as possible during a few tightly scripted hours, then continuing outward toward the Kuiper Belt. That choice turned the encounter into a one-time event. There would be no second pass, no return visit to capture a missed image or redo a failed measurement. If a single command sequence went wrong, if a protective safe mode triggered at the wrong moment, the opportunity that had taken nearly a decade of flight and far longer of planning would be reduced to fragments. Seen from this angle, a mission that almost never happened is not just about early cancellations and budget threats. It is also about the continued possibility of failure embedded in every stage. Before launch, it could have remained on paper. After launch, the rocket could have failed. After Jupiter, a navigation error could have spoiled the flyby geometry. Near Pluto, unseen dust could have struck the spacecraft and ended the story in silence. Each of those contingencies stayed merely possible. The mission continued, but the fact that it did so does not erase the fragility that was always there. It simply means that, against long odds of indifference and complexity, enough things went right for a brief alignment between a small machine and a distant world. During the years when New Horizons slept between checkouts, Pluto continued its slow movement around the Sun. The two were not in conversation. One followed an orbit set at the birth of the solar system. The other followed a trajectory calculated by a species that had only recently learned to leave its own planet. For most of that shared time, neither knew the other existed in any meaningful sense. And yet, from our point of view, the mission created a link, a narrow path of intent laid across an indifferent geometry. A deliberate line drawn from a room on Earth to a point in space where, until then, no close human attention had ever been directed. New Horizons is often described in terms of firsts. The first mission to Pluto, the first visit to the Kuiper Belt, one of the fastest spacecraft ever launched. Those descriptions are accurate, but they are not the most unsettling. More quietly, it is one of the very few times our species has chosen to spend decades preparing to glance. Just once. At a world it had already decided was unimportant. That choice did not arise from inevitability. It came from a series of fragile decisions, each of which could have gone the other way. The spacecraft that finally rushed past Pluto was, in that sense, not just a machine of aluminum and electronics, but a trace of how briefly our priorities aligned with something that lay far outside our usual concern. By the time it arrived, the arguments over whether Pluto was a planet or a dwarf planet had largely played out. What remained was a small, silent craft, moving too fast to stop, approaching a world that had never asked to be classified in the first place. The closer the craft came, the less our arguments about names mattered. What had been an abstract point with a disputed label was about to answer, in its own quiet way, a question no vote could settle. As the approach phase unfolded, Pluto first appeared to New Horizons the way it had always appeared to us from Earth. A small, bright dot set against black. Then, almost imperceptibly, the dot began to swell. Over weeks, the images sharpened from a featureless speck into a tiny disk with hints of shading. For the first time since its discovery, Pluto was no longer just a moving point. It had a face, even if that face was still blurred. By early July of the year 2015, the changes from one day to the next were obvious. Structures that had looked like random blotches began to hold their shapes from image to image. Boundaries between light and dark regions stayed put. The world was becoming consistent. On the day before closest approach, New Horizons sent back a black and white frame in which Pluto nearly filled the field of view. Taken from a distance of roughly 476,000 miles, or about 768,000 kilometers, above its surface. For a spacecraft still rushing inward at immense speed, this was already an intimate view. Beside Pluto, its large moon Charon also slid into focus. Charon's globe resolved into a muted, grayish surface cut by fractures and canyons, with a darker cap near one pole. Pluto, in contrast, showed a striking contrast of bright and dark, a patchwork of regions that seemed to belong to different categories of terrain entirely. Even before anyone knew their full meaning, the difference between primary and moon was obvious. One world with a quiet, austere face, another holding something that looked disturbingly like a symbol. At the center of Pluto's disk, a bright shape began to dominate the images. It was irregular but unmistakable, a pale region with two rounded lobes joined together. On screens in control rooms and offices on Earth, it quickly picked up a nickname, the Heart. As resolution improved, this heart did not fade into noise. It became sharper. Its edges grew crisp, the left lobe, smooth and light, contrasted with more mottled terrain elsewhere. For decades, Pluto had been treated as a leftover. Now it appeared to be offering a single, bold feature that demanded explanation. A bright, smooth expanse, bordered by darker, more complex lands. To some eyes, it looked welcoming. To others, unsettling. A shape that simple, that centered on a world that distant, was not part of anyone's prior model. Day by day, as New Horizons coasted inward, the cadence of new images increased. Weekly releases became daily, then more frequent. Each set of frames revealed fresh details. The limb of Pluto edged by what looked like haze. Subtle variations in color across the surface. Patterns of pits and troughs in the bright region. Charon revealed a great dark patch near its north. A kind of stain spread across its pole, with brighter fractured terrains to the south. For the team, and for those watching from afar, there was a quiet dislocation in this process. The world they had expected to see was a cratered, static sphere, variations smoothed by age. Instead, the incoming frames suggested structure, boundaries, perhaps even processes that had not yet finished. The approach did not just refine earlier assumptions, it began to contradict them. The approach timeline itself was unforgiving. The closest passage past Pluto had been set years in advance, a flyby in the middle of July of the year 2015, at a distance of about 7,750 miles, roughly 12,472 kilometers. Above the surface, there was no opportunity to adjust the date for better lighting or more comfortable scheduling. Orbital mechanics, not human preference, chose the moment. As that date drew near, the spacecraft was placed on a meticulously rehearsed sequence. For many hours around closest approach, New Horizons would not listen to Earth. It would turn its main antenna away to point its cameras and instruments directly at Pluto and Charon. No commands would be sent during that time. Mission Control would have no real-time confirmation that any of it was working. The distance imposed its own kind of silence. At Pluto's range from Earth, a radio signal traveling at the speed of light needs about 4.5 hours to cross the gap in one direction. Every image, every packet of data, would spend almost an entire evening in transit, long after the events it recorded had already happened. When the team watched the first high-resolution frames arrive, they were not witnessing a live encounter, but reading a record of something that had unfolded many hours before. In the final days, the images took on the feel of an approaching shoreline. Features that had been indistinct patches revealed themselves as mountains casting sharp shadows, as long troughs, as smooth expanses where impact craters seemed suspiciously scarce. The bright left lobe of the heart, later named for Pluto's discoverer, resolved into a vast plain with a texture like cracked glaze. The darker right lobe hinted at layered terrain and complicated history. Charon, too, gained relief and depth. The dark polar region appeared as a cap with a sharp boundary, its color likely the result of material processed by radiation and transported by seasonal cycles. Elsewhere, huge canyons cut across the moon's face, their scale hinting at internal forces long past. Moon and primary were clearly related, yet each bore scars that did not match the others. From a distance, worlds often look interchangeable, circles of light, similar color, similar brightness. As new horizons drew closer, that illusion was stripped away. Pluto and Charon were no longer entries in a table. They became particular. One had a heart of nitrogen ice and complex color. The other had a muted shell, split by immense chasms and capped in red. They shared an orbit and a center of mass, but not a single. Simple story. There is something quietly disquieting about watching a world materialize in this way. Every new pixel carries a small correction to prior belief. The more detail appears, the more obvious it becomes that the earlier picture was not just incomplete, but deeply wrong in its tone. What had been imagined as a frozen relic looked, increasingly, like a place where time had not quite finished its work. On the day of closest approach, the spacecraft executed its plan without feedback from home. It swept through the Pluto system at high speed, its instruments rotating in carefully timed motions, tracking targets it had never seen before this year with that precision. While it did that, Earth could only wait, armed only with knowledge of previous tests and the hope that no unmodeled dust or glitch would interfere. For roughly 22 hours, there was no word. The mission team could calculate the spacecraft's position. They could estimate its orientation. They could predict, to within seconds, when it would turn its antenna back toward Earth and begin to speak again. But throughout that interval, Pluto's new face existed only in the memory of a passing machine, held in solid-state recorders billions of miles away. When the carrier signal finally returned, a simple tone confirmed survival. The details came later, over months. Bits of the encounter trickled back through the darkness. The total science return from the Pluto flyby amounted to on the order of 6.25 gigabytes of data, transmitted at rates of only about 1 to 2 kilobits per second, using a high-gain antenna and the most sensitive receivers available on Earth. At that pace, clearing the onboard memory took roughly 16 months. In a world accustomed to instant images from nearby planets and from orbiting satellites, this slow return felt almost archaic. Each file had to be scheduled, sent, checked, then backed up. Any retransmission cost more time. The most dramatic images were prioritized early, but some of the most subtle measurements arrived many months after the spacecraft had already moved far beyond Pluto's orbit. This long delay had an odd consequence. For more than a year, Pluto's true nature was not revealed in a single moment, but in a series of partial unveilings. A new mosaic here, a spectral map there, A refined topographic model months later. Each batch of data adjusted the picture, added a nuance, overturned a convenient simplification. What New Horizons gave us, then, was not just resolution in the technical sense. It was resolution as a slow confrontation with what had been assumed. The world that emerged from those packets was not small in any meaningful way. It possessed towering water ice mountains, a vast basin of convecting nitrogen ice, layered hazes arcing above the limb, and a history that refused to compress neatly into the category of dead. Was. Yet throughout the approach, Pluto itself remained indifferent to this shift. It turned once every few days, keeping the same rhythm it had held long before any spacecraft existed. Whether we watched or not, whether data arrived or not, the plains froze and flowed. The atmosphere thickened and thinned. Charon continued its locked dance around their shared center. In that disconnect lies the quiet power of the approach. A machine built for a single encounter, carrying the weight of our expectations, flew past a world that had never depended on being seen. As Pluto came into focus, it did not change. We did. What changed, once the first detailed images were assembled, was not simply our map of a distant surface. It was the range of behaviors we had quietly decided a small, frozen world was allowed to have. When the first global mosaics came down, Pluto did not look like the minor residue of a finished system. Across the illuminated hemisphere, there were boundaries as sharp as coastlines, textures that hinted at motion, and contrasts that belonged to a world still doing work. At the center of the disk lay the bright plane we now call Sputnik Planitia, smooth and pale against darker uplands, a shape carved into a body only about 2,377 kilometers across. For something that small, this expanse was disproportionate, as if an entire geological argument had been compressed into a single feature. The plane was not merely bright, it was unnervingly clean, in region after region within its boundaries. New Horizons could not find the overlapping scars of ancient impacts that quilt most old surfaces in the outer system. Craters exist, but they are sparse, isolated, sometimes half-buried. Models based on the rate of impacts in the Kuiper Belt translated that scarcity into time. An estimated surface age of less than 10 million years, with some portions perhaps younger than a single million. On a world more than 4 billion years old, this is the geological equivalent of fresh paint. Closer inspection showed why that youth might exist. Sputnik Planitia is not a static ice sheet. High-resolution images revealed it broken into a patchwork of polygonal cells, each tens of kilometers across, with shallow troughs marking their boundaries. Numerical models suggested that those cells are the surface expression of slow convection in a thick layer of nitrogen ice, warmed slightly from below. Cooled at the top, the ice rises at cell centers and sinks at the edges, turning the plane into a frozen, planet-sized lava lamp. The sizes of those cells, roughly 16 to 48 kilometers across, match what would be expected for such overturning. In other words, Pluto is moving material around, not in sudden eruptions or violent tectonic shifts, but in a slow, persistent circulation that erases old marks and writes new ones. A process like this cannot run on a world that has entirely given up its internal energy. It requires a heat source, a reservoir, a mechanism that has been quietly at work while we assumed everything had frozen. Along the edge of the plane, nitrogen glaciers appear to flow outward and downward into adjacent valleys, their surfaces marked by gentle ridges and streamlines. In some places, blocks of darker, higher standing, water ice seem to float in the nitrogen like icebergs in a sea, gathered along the cell boundaries where sinking motion would naturally corral them. These are not the features of a surface simply preserving its earlier state. They are signatures of an ongoing conversation between interior and exterior. Beyond Sputnik Planitia, the surprises continued. To the south of the bright heart, a range of mountains rises from the plains, their peaks standing as tall as about 6 kilometers above the surrounding terrain. At Pluto's surface temperature, water ice is as strong as rock, and these peaks are made of it, not of nitrogen. They are not piles of accumulated frost. They are structural, rooted blocks of the crust pushed up into rugged chains. Mountain ranges demand explanations. On Earth, they form where plates collide or stretch. On some icy moons, they trace the edges of ancient fractures or upwellings. On Pluto, without giant neighbors to drive tides, their energy source is less obvious. They are simply there, insisting that at some point in the past, the crust was forced to move in ways that required strength, not brittle collapse. The dead world we had imagined would not bother with such architecture. Superimposed on this topography is an atmosphere that refuses to match its thin reputation. New Horizons revealed a delicate envelope of gases, dominated by nitrogen with traces of methane and carbon monoxide, arching well above the surface. Against backlit space, the spacecraft's cameras saw it not as a featureless veil, but as a finely layered structure on the order of 20 distinct haze layers, stacked all the way up to altitudes greater than 200 kilometers. Those layers are not static bands painted on the sky. They are maintained by chemistry, sunlight, and circulation. Methane and nitrogen molecules are broken by ultraviolet radiation and energetic particles, recombining into more complex hydrocarbons that clump into tiny haze particles. As those particles settle downward, they build the layered structure, interacting with winds and topography, casting long blue shadows when the sun sinks low behind the horizon. An atmosphere this sculpted is not the mark of a world that has simply exhaled once and stopped. All of this happens under a pressure at the surface that is only a tiny fraction of Earth's. At incredibly low temperatures, where nitrogen and methane must constantly choose between being gas and frost, the atmosphere can collapse onto the ground as Pluto moves farther from the sun and re-vaporize as it comes closer. Even its presence is a phase in a cycle, not a permanent state. It is precarious, temporary, but very much alive in its own way. Seen together, these elements form a pattern that is difficult to fit into the old story. A convecting nitrogen sea with cells still overturning, glaciers that flow, mountains built of water ice strong enough to hold their shape, haze stacked into dozens of layers reaching a substantial fraction of the body's radius, craters missing where they ought to be plentiful. None of these features, by itself, completely defies expectation. It is their combination, packed onto a small object in the distant Kuiper Belt, that makes the earlier label of dead feel less like a conclusion and more like a confession of limited imagination. The deeper discomfort arrives when we notice what our surprise says about us. Pluto did not become active when New Horizons arrived. Its plains did not start convecting for our benefit. Its mountains did not rise in anticipation of cameras. The processes we now rush to model have been operating for spans of time longer than our entire written history, untouched by our categories. Our astonishment is not a property of Pluto. It is a measure of the gap between the universe and the stories we told about it. There is an almost clinical calm in the data themselves. Topographic maps, temperature profiles, composition spectra, counts of craters per square kilometer. They sit in plots and tables, stripped of drama. Only when we step back and recall what was expected does the tension emerge. We had built a framework in which size, distance, and composition seemed enough to predict whether a world could still be doing anything interesting. Pluto fits none of the should statements that would normally permit such complexity. And yet here it is, quietly redesigning its own surface. In that sense, Pluto is not just a scientific outlier. It is a reminder that any rule about where life, activity, or change are allowed to exist is provisional at best, we are inclined to draw lines inside this orbit. Maybe oceans, beyond that distance. Only ice and stone. Above this mass, internal heat. Below it, thermal exhaustion. Each new exception is an invitation to redraw the line, but also a warning that the line itself may be a comfort more than a truth. New Horizons did not see the entire globe at equal clarity. The hemisphere turned toward the spacecraft during closest approach is mapped in high detail. The far side remains blurred and ambiguous. Some features glimpse the limb and disappear. Some processes are inferred from hints rather than directly seen. Even after a successful flyby, there are regions of Pluto that remain almost as abstract as the entire world once was. That asymmetry feels uncomfortably familiar. We rarely see anything completely, whether it is a planet or a person. We build models from the hemisphere that happens to face us at the moment we look. The danger is not in beginning there. It is in forgetting how partial that view is, and how easily it can be mistaken for the whole. On Pluto, the cost of that forgetting was decades of assuming stillness where motion persisted. The heart-shaped plane, the convecting cells, the mountains, the haze layers, the resurfaced terrains, all of them were real, long before a spacecraft photographed them. What changed with New Horizons was not the fact of their existence, but our willingness to accept that such a combination could inhabit a place we had written off. There is no moral in that. At least not a comforting one. The universe is not sending a message about resilience or hidden potential. Pluto does not teach anything. It simply occupies a set of physical conditions and follows from them in ways we did not predict. The lesson, if there is one, lies on our side of the radio link, a recognition that our categories are smaller than the reality they try to contain. What appeared in those first resolved images was not a world clawing its way back from irrelevance, but a world that had never been irrelevant in the first place. It was we who temporarily reduced it to a leftover, a frozen scrap on the margins of a diagram. When the data arrived, that reduction failed. The world itself did not object. It continued its long orbit, its slow cycles of freezing and sublimation, its quiet rearrangement of ice and rock. The only thing that could be called into question was our sense of how certain we are allowed to be about places we have never truly seen. The bright plane at Pluto's center is where that certainty finally lost its grip. We had drawn our lines about what a small world could be, and Sputnik Planitia stepped calmly across them. From afar, it looked simple, the left lobe of a pale heart, smooth and bright against the darker crust. Up close, that simplicity dissolves. Sputnik Planitia is a basin the size of a small continent, an ellipse roughly 1,400 kilometers by 1,200 kilometers in extent. Its surface area on the order of several million square kilometers. It is filled, not with rock, but with volatile ice, mostly nitrogen, blended with carbon monoxide and methane, frozen into a sheet thick enough to behave like a very slow, very cold fluid. The basin itself lies lower than its surroundings. Topographic reconstructions from stereo images suggest its floor sits roughly 3 to 4 kilometers below adjacent terrain, a depression later flooded by those bright ices. In a traditional story of planetary formation, such a lowland would simply collect debris and stay still. On Pluto, the opposite seems true. The more closely we look, the more the basin appears to be the restless part. Across much of Sputnik Planitia, the surface is tiled by irregular polygons. Each cell spans tens of kilometers, with an average width of about 33 kilometers from center to center. Their edges are marked by narrow troughs, sometimes occupied by darker material or by clusters of hills. At the scale of the spacecraft's images, the pattern looks uncannily like the top of a simmering pot that has been frozen mid-boil. Models built after the flyby point toward convection as the cause. Warmth from Pluto's interior modest, but not gone, seeps upward into the nitrogen ice. Slightly warmer ice beneath becomes buoyant and rises at the centers of the cells, spreads outward, cools, then sinks back down along the margins. The vertical relief of this overturning is on the order of 100 meters from cell center to edge. While the ice layer itself is estimated to be several kilometers thick, perhaps between 3 and 10 kilometers in many regions, the flow is slow, with calculated velocities of only a few centimeters per year. Yet over millions of years, that is enough to recycle the surface repeatedly. This is not a decorative skin. It is the visible top of a system that is transporting material and heat over geological time. The near absence of impact craters within the plain suggests that this overturning has wiped away older scars, leaving a surface whose age, in some parts, is less than 10 million years, and perhaps in places as young as a small fraction of that, on a body more than 4 billion years old. That youth is not an accident. Something has been working here, persistently. While we were assuming sleep, along the margins of Sputnik Planitia, the ice behaves in a more familiar way. From the higher, darker uplands of the eastern lobe of Pluto's heart, streams of bright material descend into the basin, carving shapes that look like glaciers frozen in mid-flow. Some of these tongues merge into the convecting plain, their fronts broken and jumbled where they meet the churning nitrogen. Others thread into side depressions, pooling in smaller basins that have their own subdued polygonal patterns. Embedded within the plain are scattered blocks and hills of darker, more rugged ice. Many of these are several kilometers across, clusters of what appears to be water ice crust detached from nearby highlands. Because water ice is less dense and more rigid than nitrogen ice at Pluto's temperatures, these blocks behave as floating islands, carried slowly by the convective flow and gathered along cell boundaries like driftwood at a shore. Some chains of hills trace the paths of inflowing glaciers, as if fragments of the old crust were torn away and advected into the basin. Here, motion and stillness are layered on one another. The nitrogen sea moves, overturns, and resurfaces itself. The water ice blocks ride that motion but retain the memory of the older landscape they came from. Underneath both, the impact basin that may have started this story remains anchored in the deeper crust, a fixed scar partly hidden by later deposits. Sputnik Planitia is less a single feature than a stack of histories, frozen together into one shape. The origin of the basin itself is still debated, but one leading scenario begins with a collision. In this picture, a body, perhaps a few hundred kilometers wide, struck Pluto early in its history, excavating a cavity on the order of 1,000 kilometers across and a few kilometers deep. Over time, that low area became a trap for volatile ices. Nitrogen and carbon monoxide condensed there preferentially, because slightly higher surface pressure and slightly lower temperatures favored deposition in the depression. As more ice accumulated, the load deepened the basin further, drawing in still more frost in a slow feedback loop. What makes Sputnik Planitia especially unsettling is that this accumulation seems to have done more than reshape a local landscape. By filling the basin with a thick, dense layer of nitrogen ice, Pluto altered its own distribution of mass so strongly that the entire dwarf planet appears to have rolled. Models of Pluto's inertia suggest that a load like Sputnik Planitia can drive a reorientation of tens of degrees, perhaps around 60 degrees, bringing the basin into its current position close to the line connecting Pluto and Charon. If that interpretation is right, then the bright left lobe of Pluto's heart is not just a mark on the surface, it is a weight heavy enough, in gravitational terms, to have leveraged the whole world into a new orientation. A single basin, filled with frozen gas, would have forced the crust and interior to realign with the tidal pull of its moon. The heart, in other words, may have turned the body. This idea carries another implication. For a load like Sputnik Planitia to act as a positive gravity anomaly rather than a negative one, there must be extra mass at depth, not just a depression filled with light material. One way to provide that mass is to place a layer of denser liquid water beneath the basin, thinning the ice shell above and replacing lower density rock with higher density ocean in that region. Several studies using Pluto's shape and tectonic patterns point toward an ice shell that may be roughly several tens of kilometers thick, with an underlying global or regional ocean contributing to the mass balance. So beneath a plane of convecting nitrogen, there may be kilometers of icy shell, and beneath that, a buried sea. None of this was required by our prior categories. A dwarf planet far beyond Neptune, with a radius barely over 1,000 kilometers, was not supposed to be a candidate for a long-lived subsurface ocean. Yet the gravitational and tectonic fingerprints around Sputnik Planitia keep nudging the models in that direction. On the surface, other details hint at a restless environment. Near the northwestern margin of the basin lies a field of low, regularly spaced ridges interpreted as dunes, formed by winds dragging grains of methane ice across the plain. Their spacing is on the order of less than a kilometer, aligned roughly perpendicular to nearby wind streaks, suggesting that even in air as thin as Pluto's, motion is enough to organize material into patterns over time. Elsewhere, chains of pits dot the surface, deeper and wider toward the cell edges, shallower near the centers. These are thought to form by sublimation, nitrogen slowly departing the solid, molecule by molecule, leaving behind dark residues or deeper voids. Their size distribution allows estimates of how quickly the ice is moving from center to edge, again arriving at velocities of centimeters per year rather than meters. A speed that is glacial even by glacial standards, and yet is not zero. Taken together, the numbers are almost comically modest. Centimeters per year, kilometers of thickness, tens of kilometers across, millions of years. None of this sounds dramatic beside supernovae or black holes, but it is precisely the quiet scale that makes Sputnik Planitia so difficult to dismiss. Over enough time, a few centimeters per year redraw a world. Over enough depth, a few kilopascals of stress fracture an ice shell and help decide where faults and chasms will appear. What sits at the western lobe of Pluto's heart, then, is a kind of slow machinery. An impact or accumulation event created a depression. Volatile ices pooled there, thick enough to flow. That load altered the planet's balance, possibly tilting the entire body until the basin settled into a position of gravitational preference. Convection within the ice continues to erase and rebuild the surface, and the basin's weight may still be influencing tectonic patterns far beyond its visible rim. There is an easy temptation to read symbolism into the name. A heart that is not warm but cold. A symbol of love that is, in reality, a consequence of impact, freezing, and slow internal strain. The resemblance invites metaphor. The physics quietly shrugs it off. The shape we recognize so quickly is simply the projection of deeper processes operating over scales of space and time we rarely inhabit in thought. Still, it is difficult to look at Sputnik Planitia and not feel a slight unease about how we decide which parts of a world matter. Before New Horizons, Pluto's heart did not exist in our minds. The region was there. Of course, the basin had formed. The ice had convected. The possible ocean had done its work on the planet's inertia, but our maps were blank in that space. We had no reason to imagine that the most active zone on Pluto would also be the one that, when seen from afar, would trace out a shape humans instinctively read as significant. In that coincidence lies a small, quiet trap. It is easy to think that a shape that feels meaningful must have been placed there for us, or that a feature that reorients a planet must surely carry a message. Sputnik Planitia offers a stricter lesson, a random collision, a volatile inventory, a cooling interior, and the equations of ice flow are sufficient to produce a basin that both turns a world and mimics a symbol. Meaning arrives later, from the minds that name it. The basin will continue to evolve long after those names are forgotten. Nitrogen will keep freezing and sublimating as Pluto moves through its elongated orbit. The atmosphere will thicken and thin. The pattern of convection cells will shift and rearrange. Dunes may migrate. Pits may deepen. Blocks of water ice may slowly drift from one cell to another. The heart will change its details while keeping roughly the same outline. The way a human face ages without losing its basic shape. From the perspective of the ice, there is no mystery here. Energy gradients drive motion. Gravity shapes the basin. The interior provides just enough heat to keep the system from seizing up. From our perspective, though, Sputnik Planitia is a point where the universe's indifference and our hunger for structure intersect. We projected simplicity onto Pluto, and this basin quietly refused to comply. What sits at the center of Pluto's visible disk is not a sentimental emblem, and not a monument to resilience. It is a cold, bright contradiction, a place that should have been quiet by every rule we trusted, yet instead is busy enough to erase its own past, heavy enough to tip its world, and deep enough to hint at an unseen ocean beneath. The weight that could tilt a world did not arise from a flat sheet of ice alone. For Pluto to carry a basin like that and keep reshaping it, something underneath had to be strong enough to hold, and warm enough not to quit, west of the bright plain. The first surprise is vertical. Rising out of the boundary between Sputnik Planitia and the darker highlands are ranges of jagged peaks, their silhouettes sharp against the haze-lit sky. These are not little ripples in frost. The Norgay Montes, the range nearest the plain, climb to heights of roughly 3 4/10 kilometers above their surroundings, their slopes casting long shadows across the nitrogen. Behind them, the Hillary Montes stand even higher, reaching roughly 3 1/2 kilometers from base to crest. At Pluto's surface temperature, water ice is not the gentle material we know on Earth. With average conditions near 44 Kelvin and extremes ranging from roughly 33 to about 55 Kelvin, water there behaves mechanically more like stone. The mountains flanking Sputnik Planitia are built from that rock-hard water ice, rising out of a bed of softer nitrogen and methane frost. Their very existence implies a crust thick and strong enough to support steep, sustained relief without simply flowing flat. On a body as small as Pluto, that is already an argument against exhaustion. Building a mountain several kilometers high out of rigid ice requires forces that act over long periods, uplift, faulting, or the piling up of material from below. Holding that mountain in place then demands a lithosphere that has not sagged into equilibrium, that still remembers the stresses that shaped it. Further south, another structure complicates the picture. Right Mons, an immense, roughly circular massif, rises from a low-lying region southwest of Sputnik Planitia. It is about 150 kilometers across and on the order of 4 kilometers higher than the terrain around its base, with a broad, central depression near its summit. The flanks of Right Mons are covered in a tangled field of hummocks and mounds, giving it a texture unlike any familiar volcano on Earth or Mars. Interpreted as a possible cryovolcano, Right Mons would be a conduit through which material from Pluto's interior once reached the surface. Instead of molten rock, the eruptions would have carried slurries of water, ammonia, and other ices, extruding them in slow, thick flows that built up the edifice layer by layer. The near absence of impact craters on its sides suggests that Right Mons is geologically young, with some estimates placing its age at less than 1 billion years. In a system once thought to have finished cooling billions of years ago, this youth is awkward. If Pluto can construct a mountain several kilometers high in the relatively recent past, Then some reservoir of internal energy must have remained available long after our simple models declared the interior cold and inert. Where could that energy come from? Pluto is too small and too isolated to be heated by tides the way some moons are. The most straightforward source is slower and more subtle: the decay of radioactive elements in its rocky interior. Isotopes of uranium, thorium, and potassium embedded in the core release heat as they decay over billions of years, warming the base of the ice shell from below. If that heat is strong enough, and the shell is thick enough, ice near the bottom can melt to form a layer of liquid water, overlain by a convecting lid of solid ice. The same radiogenic power that slowly cools larger planets from the inside can, in a smaller body, maintain a subsurface ocean and soften the deep crust, allowing large-scale stresses to build and release as fractures, uplifts, or cryovolcanic eruptions. Thermal evolution models explore two extreme histories. In a so-called cold start scenario, Pluto forms slowly, accumulating icy material over time, never getting hot enough for widespread melting. In such models, any ocean that might appear tends to freeze and thicken with age, leading to early compression of the surface, followed by later extension as the shell adjusts. In a hot start scenario, Pluto forms quickly, trapping enough energy from impacts and initial radioactivity to melt large portions of its interior early, creating a substantial ocean that can persist for billions of years if insulated by an ice shell and reheated from below. The patterns seen on the surface favor the second story. Across Pluto's crust, there is abundant evidence of extension fractures and troughs, implying that the shell has been pulled apart, while clear signs of large-scale compression are conspicuously lacking. That is easier to explain if the interior began warm and remained warm enough to keep the ocean from fully freezing, causing the shell to expand slightly over time and crack. In that framework, mountains and chasms are not relics of an early predis brief phase. They are symptoms of a long, ongoing imbalance between interior heat and exterior cold. The temperature contrast that drives this imbalance is severe. Above, the surface hovers tens of degrees above absolute zero, bathed in faint sunlight. Below, at the ice rock boundary, radiogenic decay can maintain temperatures hundreds of degrees Kelvin higher than the surface, enough to keep water in a liquid state under pressure. Between those layers, the ice shell transports heat outward, deforming slowly under its own weight and the stresses imposed by changing loads like Sputnik planitia. Mountains of water ice form where that shell is forced upward or fractured. Some may be the edges of great blocks lifted by underlying buoyant ice. Others may be piles of material extruded from depth, now frozen in place. The Norgay and Hillary ranges, rising to heights of several thousand meters along the edge of the plain, are almost certainly connected to the stresses imposed by the Sputnik Basin's weight and by broader tectonic patterns that girdle the dwarf planet. From orbit, their jagged silhouettes are shocking, mostly because of where they are. A similar range on Earth or Mars, in warmer conditions and nearer the Sun, would feel natural. Another example of a familiar type, on Pluto, at distances where sunlight is diluted to a faint glow and surface temperatures plunge into the tens of Kelvin. Such rugged topography feels like a violation. That feeling is misleading but instructive. The physics of rock and ice do not care how we have arranged our mental maps. If internal heat and material properties allow a body to carry towering structures, those structures will appear wherever conditions permit. Our discomfort comes from having quietly decided that complexity belongs in some parts of the solar system and not in others. Reitmans pushes that discomfort a step further. If it is indeed a cryovolcano, then at some point in the last few 100 million or billion years, material from deep within Pluto rose and erupted onto the surface. The summit depression, roughly 45 kilometers across and several kilometers deep, looks like a caldera left by collapse after repeated eruptions, emptied a subsurface reservoir. Around its flanks, the hummocky textures could be the frozen remains of thick, viscous flows. Each one a snapshot of internal motion made solid. There is no spectacle here in the ordinary sense. If you could stand near Right Mons during an eruption, you would not see fire. You might watch a slow extrusion of slushy ice, creeping downslope over days or weeks, radiating heat only slightly above the surrounding frost, yet scaled to Pluto's environment. That would be an event as dramatic as any lava fountain on Earth, a direct statement that the interior is still capable of moving matter across tens of kilometers of vertical distance. The presence of such features does not guarantee that any subsurface ocean is still entirely liquid. Portions may have frozen, thickening the shell and altering its stress state. But the combination of extended tectonic structures, loaded basins, mountains at the edge of volatile plains, and possible cryovolcanoes supports the idea that Pluto's interior has not been static for most of its history, and may still be adjusting today. If that is true, then Pluto is not just carrying relics of an earlier, warmer era. It is a world where extremely slow processes continue to play out in an environment that we would instinctively label as finished. Deep inside, radioactive atoms continue to split and rearrange, releasing tiny packets of energy. Those packets, accumulated over aeons, keep water from freezing solid everywhere, keep the shell from relaxing completely, keep faults and basins and mountains from settling into a final, flattened state. There is a quiet kind of unease in realizing how much can happen with so little. A thin trickle of internal power, spread across a small globe, manages to push up mountain ranges kilometers high, maintain an ocean beneath ice tens of kilometers thick, and drive convection in nitrogen plains millions of years after they first formed. Each number in that chain, each kilometer, each Kelvin, each million years is modest on its own. Together, they are enough to overturn the assumption that small, distant, and cold must mean simple. Look long enough at the mountains west of Sputnik Planitia and the categories begin to blur. Are they the edges of a basin? The boundaries of an ancient impact? The rims of blocks that have shifted as the shell expanded? Or the flanks of slow eruptions from below? The most honest answer for now is that they are likely some combination of all of those things. Pluto's water ice is acting as crust, as bedrock, as tectonic plate, and as volcanic material, depending on depth and temperature. In that complexity, there is no hint of intention, only the consequences of starting conditions and physical laws. Yet for us, used to telling ourselves that we understand where energy is allowed to flow and where change is permitted to continue, these mountains and possible volcanoes are a quiet rebuke. They sit beyond Neptune, under a faint sun, at temperatures where most substances we know would be brittle, and they insist, with their very shape, that the story is not finished. The internal heat that raised them will keep fading. Radiogenic sources weaken over billions of years, and any ocean beneath the shell will eventually freeze entirely if nothing else intervenes. There will be a time, long after our brief presence is gone, when even Pluto's deep interior falls still, and mountains stop rising, and basins stop shifting. But the point at which we encountered this world is not that end point. We arrived while the system was still in motion, standing back from the maps. It is hard not to feel the contrast. At the edge of a system we thought we had classified, a small, dim object carries mountains of rock, hard water, ice, basins that can tip a world, and evidence of eruptions that draw their power from atoms splitting slowly in the dark. The labels we used for it, small, cold, minor, are still technically correct. They are also no longer sufficient. Color is where that insufficiency stops being abstract. On Pluto, it is the first thing that tells us The surface is not just shaped, but argued over, layer by layer, by light and time, seen in true color. Pluto is not white, or gray, or even uniformly red. The global mosaics from New Horizons show a patchwork, a dark, deep red band hugging much of the equator, bright, almost white plains in the heart, bluish tints near some limb regions, and a muted yellow cast at the northern pole. It is the kind of palette that invites metaphor, but beneath it lies something colder and more precise. The dark equatorial band, once called Cthulhu and now named Belton Regio, stretches almost halfway around the planet. It is an elongated stain along the equator, roughly 3,000 kilometers long and about 750 kilometers wide, with a total area on the order of nearly 1.8 million square kilometers. Its surface is among the darkest on Pluto, pitted with craters, ridges, and occasional smoother patches. To the human eye, in enhanced images, it reads as a rusty, almost black red. That red is not paint. It is chemistry. Pluto's atmosphere is thin, but not empty. It is dominated by molecular nitrogen, with smaller amounts of methane and carbon monoxide, along with trace hydrocarbons like acetylene and ethylene that New Horizons detected in ultraviolet spectra, high in that tenuous air. Ultraviolet sunlight and energetic particles break apart the simple molecules and let them recombine into more complex chains. The resulting fragments clump into tiny solid particles, often modeled as tholins, complex organic solids that are neither gas nor ice, but something in between, carbon-rich and light-absorbing. Those particles do not stay suspended forever. New Horizons saw haze extending up to at least 200 kilometers above the surface, arranged in on the order of 20 distinct layers. But gravity is patient. Over months and years, haze particles settle, falling through the thin air and eventually landing on ice. There, they build up as films and coating, darkening whatever they cover. Laboratory experiments using Titan and Pluto haze analogs suggest that many tholin particles are not simple spheres, but aggregates, clumps perhaps around a micrometer across, built from monomers tens of nanometers in size. These are the right scale to scatter blue light, giving Pluto's atmosphere its thin blue ring when backlit, even if the particles themselves may be gray or reddish. From a distance, that scattering becomes a sky. Up close, the same particles are dust, accumulating slowly on the ground. Belton Regio is one of the main places where that dust seems to have been allowed to collect without much interference. Its low reflectivity and deep red color are consistent with a thick coating of complex organics, probably including tholin-like material, over older ice and rock. Craters there are numerous, with some areas showing counts that suggest surfaces billions of years old, unlike Sputnik Planitia, which keeps resurfacing and erasing its own past. Belton Regio appears to keep what falls on it. The result is that color on Pluto carries time. Bright regions with few craters and high albedo mark places where fresh, volatile ice buries or replaces whatever was there before. Dark, redder regions with many craters record long exposure to space, repeated cycles of haze fallout, and little geological renewal. In that sense, Pluto is striped, not just by latitude, but by age. The pattern is not random. In the global color maps, the darkest, reddest terrains cluster along the equator, forming a band that the equator roughly bisects. This band lies adjacent to the bright nitrogen plains of Sputnik Planitia, whose almost white tones come from clean, volatile ices that reflect most incoming light. Between them, more neutral and bluish hues appear, where methane or nitrogen frost and exposed water ice mingle with thinner deposits of haze particles. Spectrometers aboard New Horizons mapped these differences in composition, The LISA instrument and the MVIC camera recorded how strongly Pluto's surface absorbs light at wavelengths associated with methane, including a narrow channel between roughly 860 and 910 nanometers that is particularly sensitive to methane ice band depth. Areas where that absorption is strong are not evenly distributed. Methane-rich ices cluster in certain latitudes and elevations, sometimes draped over mountain peaks as bright caps, sometimes pooled in depressions, where methane is thick and fresh. It tends to wash out the red. Where it is absent or thin, the underlying darker material shows through. Belton Regio, with its equatorial location and its rough, ancient topography, seems to sit in a regime where volatile ices sublimate away more readily and haze products can stay exposed. The red is not painted on. It is what is left when other things fail to stay. Even that picture is more complicated than the early interpretations suggested. Laboratory teams have tried to reproduce Pluto's colors by generating tholins under simulated atmospheric conditions, then comparing their reflectance spectra with New Horizons data. Some of the matches are close, but not perfect. In particular, the spectral signature of the dark red material in Belton Regio is not entirely explained by standard tholin analogues alone. The real surface may be a mixed layer, tholins, radiation, damaged methane and nitrogen ices, perhaps other complex organics, perhaps even residues from older eruptions or impacts. Color, in other words, is evidence, not a single substance. This is where Pluto's quiet contradiction deepens. On many worlds, we are used to treating color as decoration, a simple indicator of composition that we can translate into a map and then ignore. On Pluto, the colors insist on being read as the intersection of chemistry, climate, and time. The blue haze exists because the atmosphere is cold and thin but still present. The bright heart exists because nitrogen can move and pool. The red band exists because some terrains have been sitting under that haze for longer than others, slowly accumulating the universe's equivalent of soot. Over all of this, the surface temperature remains ferociously low. Pluto's mean surface temperature is about 44 Kelvin, with extremes dipping close to 33 Kelvin and rising at most to something like 55 Kelvin in brighter areas. At those temperatures, methane and nitrogen are not just cold, they are solids that can sublime directly into gas and recondense elsewhere. The haze chemistry rides on that cycle, where frozen methane warms and sublimates. It can feed the atmosphere, where it cools and condenses. It can bury organics under a thin reflective veneer. Belton Regio is not alone in bearing the marks of this interaction. Elsewhere, highlands near the equator show bright coatings on their peaks that spectral maps identify as methane frost, while their lower slopes darken toward red as tholin-rich material re-emerges. The visual effect is that of mountains dusted with pale snow above stained, older rock. The physical process is simple: cold traps at altitude, warmer conditions below, cycles of condensation and loss. The emotional effect, if we insist on having one, is stranger. The heights keep getting resurfaced. The lowlands are left to keep their memories. The haze itself is not purely a passive veil. Models of Pluto's atmospheric energy balance suggest that the haze particles, by absorbing and re-emitting radiation, may help control temperatures in the upper atmosphere, which New Horizons found to be unexpectedly cold, around 70 Kelvin, rather than the higher values predicted. In that sense, the same chemistry that darkens the surface also shapes the structure of the air, feeding back into how volatiles move and where ices can persist. Nothing in this chain of processes is designed. Photons strike molecules. Bonds break. New chains form. Particles collide and stick. Gravity pulls them down. Ice holds them briefly, then lets them go when conditions change. Over millions and billions of years, those steps produce a map that, to human eyes, divides Pluto into white, red, blue, and yellow domains. We arrive late and ask what the colors mean. The more we learn, the more the answer shrinks to something both humbling and precise. They mean that light has been interacting with matter for a very long time, under conditions that are not ours. There is a quieter realization hidden in this. If a band of dark red along Pluto's equator can encode billions of years of irradiation and climate cycles, then our earlier picture of a simple, icy remnant was not just incomplete, it was blind to an entire dimension of the world. We saw an outline and assumed uniformity. The reality is that even at the edge of the system, every patch of ground has a history written in its shade. It is tempting to assign roles, to say that the heart is where Pluto is young, and the red band is where it is old, to say that blue haze marks vitality and black plains mark decay. But those distinctions are ours, borrowed from landscapes we know. On Pluto, youth and age, burial and exposure, brightness and darkness, are all just different ways energy and matter have arranged themselves under a distant sun, tholins. In this setting, are not exotic pigment. They are what happens when simple gases are given enough time, enough photons, and enough space to recombine without interruption. They turn starlight into substance. They turn invisible radiation into something that can stain ice. They make it impossible to pretend that the outer solar system is colorless. In the end, the phrase dark red region rich in tholins is a way of saying that a place has been exposed for a long time to a universe that is constantly, quietly altering it. On Pluto, those places form a belt around the waist. They sit next to a bright nitrogen sea and under a stratified blue haze. They are not random, and they are not decoration. They are where the planet's long exposure is most visible, and where our categories, once again, had the farthest to fall. The thinnest part of Pluto is also the most stubborn. We tried to picture it as a fading trace, and found instead something that refuses to quietly vanish. Pluto's atmosphere is easy to underestimate. At the surface, the pressure is roughly 1 Pascal, on the order of 10 microbars, a tiny fraction of the air at sea level on Earth. You would call it a vacuum if you were standing there. Yet in that near emptiness, molecules still collide, trace gases still circulate, and light still finds enough matter to scatter blue around the limb. The bulk of that atmosphere is molecular nitrogen. Mixed into it are smaller amounts of methane and carbon monoxide. Measurements from New Horizons suggest that methane accounts for roughly 1/4% of the gas, with carbon monoxide at around a few hundredths of 1%. The rest almost entirely nitrogen. On Earth, nitrogen supports oceans of air and weather systems that span continents. On Pluto, the same molecule has to sustain an entire atmosphere with only a thin layer of frozen nitrogen on the ground to feed it. The vertical reach of that tenuous shell is surprisingly large. New Horizons observations saw Pluto's atmosphere extending to at least 1,000 miles above the surface, roughly 1,600 kilometers, with detectable structure far beyond what anyone had predicted. Closer in, the haze that wraps the planet forms distinct layers up to more than 200 kilometers high, with roughly 20 separate strata resolved in the clearest images. Even where the pressure is almost nothing, the architecture is elaborate. Near the ground, the air is held in place by cold. Pluto's surface sits at a mean temperature of about 44 Kelvin, with colder patches dropping toward the low 30s and warmer spots climbing into the mid-50s. At those temperatures, nitrogen, methane, and carbon monoxide can exist as either solid frost or thin gas, depending on small changes in sunlight and topography. An extra degree or two is enough to send ice into the air. A subtle cooling is enough to bring it back down. Because of that balance, the atmosphere is always provisional. As Pluto moves along its stretched orbit, sometimes closer to the Sun, sometimes much farther, the pattern of freezing and sublimation shifts. There are seasons in which more of the nitrogen lies on the surface as ice, and seasons in which more hovers above as gas. Over a single long Pluto year, the atmosphere can partly collapse and then rebuild. A slow global inhalation and exhalation measured not in months, but in decades. New horizons caught Pluto during one of the thicker phases. Radio occultation data from the REX instrument indicated that the surface pressure was roughly 10 to a little over 10 microbars, consistent with ground-based stellar occultations in the years just before the flyby. The lower atmosphere, within a few tens of kilometers of the surface, showed a temperature structure matching earlier measurements. A shallow, cold layer above nitrogen ice, warming upward into a temperature inversion. Above that lower region, however, the story changed. Prior to the encounter, some models had predicted that Pluto's upper atmosphere would be relatively warm and extended, with nitrogen escaping into space at rates that could strip away a global layer of ice several hundred meters thick over the age of the solar system. New horizons found something else, an upper atmosphere unexpectedly cold and compact, with escape of nitrogen suppressed by roughly 4 orders of magnitude compared with those earlier estimates. Instead of losing tens or hundreds of kilograms of nitrogen every second, Pluto is currently shedding on the order of only a few grams to at most a few tens of grams per second, corresponding to about 10 to the 23rd molecules of nitrogen each second, and perhaps 5 times 10 to the 25th molecules of methane, spread across the lifetime of the solar system. That amounts to only a thin veneer of lost nitrogen ice, a few centimeters thick, and a thicker but still modest loss of methane, on the order of tens of meters. The great atmospheric hemorrhage that some had envisioned simply is not happening, at least not now. The haze that fills Pluto's skies plays a role in this restraint. Ultraviolet light from the distant sun breaks apart nitrogen and methane molecules high above the surface. The fragments recombine into heavier hydrocarbons and nitriles, forming tiny aerosol particles. Those particles both scatter sunlight and absorb it, acting as a delicate thermal blanket that helps cool parts of the upper atmosphere and limit expansion. Paradoxically, the same chemistry that makes Pluto's sky glow blue in backlit images may be part of what keeps its atmosphere from boiling away. Look at the profile, and the structure is stark. Near the interface with space, densities drop off rapidly, following an exponential curve set by temperature and gravity. Deeper down, around altitudes of tens to a couple of hundred kilometers, the haze layers trace undulating sheets that can extend 1,000 kilometers across the limb. Thin but persistent. Below that, within only a few kilometers of the surface, temperatures shift in ways that seem to depend on whether Rex was looking over bright nitrogen plains or darker, more volatile, poor regions. All of this complexity hangs on the presence of a few kilometers of volatile ice spread as a skin over the crust. That layer is both reservoir and boundary. When Pluto is nearer the Sun, parts of it sublime, feeding the atmosphere and thickening the haze. When the dwarf planet moves farther out, more of the volatiles condense back onto the surface, thinning the air. There is no fixed separation between surface and atmosphere here, only a cyclical exchange. From a distance, we tended to treat this cycle as a footnote. The main story, in older models, belonged to the solid body, the ice, the rock, the possible ocean. The gas around Pluto was an afterthought, a temporary shroud that might soon freeze out anyway. New horizons forced a revision. The atmosphere is not just an adornment. It is an active part of the planet's energy budget and surface evolution, moving volatiles from one hemisphere to another, darkening some regions and brightening others, contributing to the growth and retreat of glaciers and the maintenance of Sputnik Planetia's brightness. In technical language, This is climate. Pluto has climate zones defined not by human habitability, but by the angles at which sunlight falls and the ways nitrogen responds. Models divide its surface into bands: true tropics where the sun can pass overhead, polar caps that experience decades of continuous light or darkness, and transitional belts where the terminator lingers. Each zone hosts its own balance of ice and air. Each shapes the local thickness of the atmosphere drawn above it. What makes this quietly unsettling is the time scale. Pluto takes roughly 2.5 Earth centuries to circle the Sun. In that time, its axial tilt and elliptical orbit combine to orchestrate seasons that can last longer than the existence of many human nations. During some stretches, volatile ices migrate toward one pole. During others, they retreat. The atmosphere thickens and thins, but does not simply vanish. It persists through these long cycles, changing slowly while our own histories flash by in comparison. We often reserve words like weather and climate for places we might, in principle, stand. Yet Pluto's thin breath demonstrates that these patterns do not depend on us. A world with a surface pressure measured in microbars, a sky that begins near the freezing point of nitrogen and warms into methane-rich layers tens of kilometers up, and a haze that stretches to altitudes of hundreds of kilometers still organizes its energy in structured ways. In that light, our earlier question, does Pluto even have an atmosphere, starts to sound less like a scientific puzzle and more like a confession of how narrowly we define significance. We asked if such a small, cold body could sustain air worth studying. What we met instead was a system in which a global climate, a complex haze, and a slowly leaking edge coexist under a pressure that, by our standards, barely qualifies as presence at all. The atmosphere will not last forever. Radiogenic heat in the interior will continue to fade. The inventory of surface volatiles can change through impacts or slow escape over very long timescales. Pluto may indeed end up with most of its nitrogen locked in place, its breath reduced to almost nothing. But that theoretical end state is not where we encountered it. We arrived at a moment when its thin air was still deep enough to bend radio waves, rich enough to carry trace hydrocarbons, and structured enough to throw layered shadows across mountains. If there is a quiet lesson in Pluto's thin breath, it may be this: a world does not have to be large, warm, or comfortable to sustain a history in its air. It only has to sit long enough in the light of a star, letting gravity hold onto a few molecules while chemistry and time do the rest. What we used to call an almost negligible atmosphere has turned out to be one more place where our sense of what should be possible was smaller than what has already, for a very long time, been true. The question that followed was simple and unwelcome. If the air and the surface are still changing, what right do we have to assume that the deep interior has already gone still? Pluto, as a whole, is small. Its diameter is a little under 2,400 kilometers, with a mean radius close to 1,200 kilometers. Its bulk density, roughly between 1 8/10 and 2 1/10 grams per cubic centimeter, tells us that it is neither a pure ice ball nor a rocky miniature of a terrestrial planet, but a mixture of both, a rocky core wrapped in a thick shell of water ice, overlain in places by more volatile ices like nitrogen and methane. For a long time, that picture ended at the boundary between rock and ice. The assumption was that the ice shell, cooled over more than 4 billion years in the deep outer system, would have frozen solid from top to bottom. Any liquid that might once have existed would have been temporary, a short-lived phase in the early history of the body, long since erased. The images from New Horizons did not show us the interior directly. They showed fractures, mountains, basins, and plains. What shifted the conversation was not what we saw underground, but what the surface implied about what must lie there. Across Pluto's globe, many of the large tectonic features are extensional. Great troughs, grabens, and chasms stretch for hundreds of kilometers, their walls parted as if the crust had been pulled outward. What is missing? Almost entirely are large-scale compressional features, no global belts of thrust faults, no obvious signs that the shell has been pushed together on a planetary scale. That imbalance matters. When water inside an ice shell freezes, it expands. If an internal ocean forms late and then completely solidifies, the shell first contracts as the ice warms and transforms, then later expands as more water freezes. Under some conditions, models show that the formation of a very thick ice shell, greater than about 260 kilometers, should create enough dense, high-pressure ice to make the planet as a whole contract. That contraction ought to leave compressional scars. On Pluto, we do not see them. One way to reconcile the geology with the physics is to reverse the story. Instead of a cold body that slowly warmed into an ocean, Pluto may have begun relatively hot, with an internal ocean present early. And that ocean may never have completely frozen. In that scenario, the ice shell thickens modestly over time as some water turns to solid, producing net expansion and extension. But it never reaches the conditions needed to form the densest ice phases that would drive contraction. Subsurface oceans are, by definition, invisible. Their presence has to be inferred from indirect signs. On Pluto, one of the strongest such signs lies under Sputnik Planitia. The basin is a deep depression, probably several kilometers below the planetary average. Yet the way Pluto has reoriented itself suggests that Sputnik has behaved not as a light scar but as a heavy weight. The basin sits very close to the line connecting Pluto and Charon, near the point opposite the Moon. That location is special for any mass anomaly. It is one of the preferred resting places. If tidal and rotational forces are allowed to roll the body until heavy features sit at energetically favorable longitudes. Detailed studies of Pluto's figure indicate that Sputnik Planitia carries a positive gravity anomaly, enough to drive a kind of slow roll known as true polar wander and bring the basin toward its present position. A deep depression filled only with low-density nitrogen ice should produce a negative gravity anomaly, not a positive one. Something denser must be lurking at depth. One way to get that extra mass is to thin the ice shell under the basin and let liquid water from a subsurface ocean rise to shallower levels, replacing lighter rock in the mass budget beneath Sputnik Planitia. Calculations suggest that thinning on the order of several tens of kilometers and perhaps close to 90 kilometers under the deepest part of the basin would be needed. That picture aligns with thermal evolution models crafted both before and after the New Horizons encounter. In one set of simulations, if Pluto's rocky core has a moderate thermal conductivity and contains a realistic inventory of radioactive elements, the heat leaking outward can sustain a liquid layer beneath an ice shell for billions of years. One family of models predicts an ocean roughly 160 or 170 kilometers thick beneath an ice shell of similar thickness, provided the shell remains only weakly convecting. More recent work, incorporating the flexing of the shell under the load of Sputnik Planitia, points to an ice shell beneath the basin between about 65 and 90 kilometers thick, with an average near 78 kilometers. Implying that any ocean there must lie comparatively close to the surface. A different study using gravity and tectonic patterns argues that Pluto could host a global ocean lurking beneath a shell between roughly 40 and 80 kilometers thick. The numbers differ because the models rest on different assumptions about the shell's viscosity, its ability to convect, and the exact distribution of mass under Sputnik Planitia. But they converge on one point. It is very hard to match Pluto's present surface without including a layer of liquid water somewhere inside. The mechanism that keeps that layer from freezing solid is simple but patient. The rocky core contains isotopes of uranium, thorium, and potassium that decay over time. releasing heat at a rate that, when integrated over the planet's volume, can sustain temperatures at the base of the ice shell well above the melting point of water under pressure. If the shell above is not too thin, and if there are substances mixed into the water that lower its freezing point, ammonia, salts, or methane hydrates, the ocean can persist for the age of the solar system. One proposed ingredient, methane hydrate, does something more subtle. In high-pressure experiments and models, methane, trapped in a clathrate lattice, has a thermal conductivity several times lower than that of ordinary water ice and a higher viscosity. A layer of such clathrate at the base of the shell would act as insulation, slowing the loss of heat from the ocean and keeping the overlying ice cooler and mechanically stronger. In that configuration, the ocean can remain liquid, while the crust above maintains large thickness variations like those inferred beneath Sputnik Planitia. None of this requires miracles. It requires a starting condition in which Pluto formed relatively rapidly, capturing enough accretional energy to melt much of its interior early, and a composition that includes a few percent of antifreeze compounds in the water layer. Given those initial states, the planet's internal cooling time stretches into billions of years, and the subsurface ocean becomes not a rare exception but an expected consequence. The problem is not the physics. It is our reluctance to allow such complexity so far from the sun. We are used to tying oceans to a narrow band, the so-called habitable zone, where starlight is strong enough to keep water liquid at the surface. Within that zone, we place our classic worlds, Earth with its open seas, perhaps Mars in its early epochs. Beyond it, we once imagined only frozen plains. The discovery of subsurface oceans on moons like Europa and Enceladus has already expanded that concept. Pluto pushes it further, out past Neptune, into a region where even calling the sunlight daylight feels generous. Under hundreds of kilometers of ice, in a place where the surface never rises above a few dozen degrees above absolute zero, there may be a global reservoir of liquid water that has outlived entire eras of our own planet's history. That water is not exposed to space. It never sees the sun. Its interface with the ice above may be locked in darkness for as long as the ocean exists. If such an ocean is there, what fills it is not only water and antifreeze. The rocky core beneath can supply chemistry, minerals, metals, and perhaps gradients in temperature or composition. Radiogenic heat does not arrive uniformly. It leaks out in patterns shaped by material properties and fracturing. Where that heat meets water, it can create environments that, in our own seas, would be called hydrothermal. On Earth, places like that host rich ecosystems, entirely independent of sunlight, feeding instead on chemical disequilibria. It would be convenient to say that this makes Pluto a likely home for life. The truth is more resistant. The presence of liquid water, rock, and energy is a set of conditions, not a guarantee. We do not know whether any pocket of that ocean has ever assembled the kind of complex chemistry that can copy itself, evolve, and persist. We may never know. Reaching such a sea would require technologies and missions far beyond a single flyby. What the possibility does challenge, even without an answer, is our habit of treating habitable conditions as something that must be rare, precarious, or confined to narrow distances from stars. Pluto is small, cold, and distant, and yet under the right starting conditions, it can carry a deep ocean for billions of years. If that is true here, it may be true for many other icy worlds scattered beyond the traditional planetary order. In the maps drawn after New Horizons, we can trace where the suspected ocean has left its mark without ever seeing it. The great fractures that run for hundreds of kilometers across the surface can be read as responses to shell expansion driven by partial freezing of water below. The orientation of Sputnik Planitia, close to the Pluto-Charon axis, points toward a heavy anomaly at depth, consistent with uplifted liquid beneath a thinned shell. The absence of compressional belts argues against the formation of the densest ice phases that would require a fully frozen interior. Put together, these lines of evidence outline something we cannot yet draw, a hidden oceanic layer, perhaps tens to more than 100 kilometers thick, trapped between rock and ice. It is as much an absence in our data as a presence in our equations. We see its edges and consequences, not its surface. There is a quiet parallel here with the way we understand anything that cannot be measured directly. We watch for distortions, anomalies, effects at the edges of what we can see. We infer the presence of something larger and more complex than the signals themselves. Pluto's ocean, if it exists, is one such inference, a volume of water that may never be imaged, deduced from a tilt in the planet's axis and the angle of its fractures. Whether or not it is habitable, that buried sea forces a shift in our sense of what a finished world looks like. We once assumed that small bodies, especially those far from the sun, passed quickly through any liquid phase and settled into cold permanence. Pluto instead offers a different arc: rapid early heating, ocean formation, slow cooling, partial freezing, ongoing tectonic adjustment, and a present in which liquid may still lie only tens of kilometers below the ice that New Horizons photographed. From the spacecraft's point of view, none of this is visible. It flew past a crust of ice and nitrogen plains, mountains and hazes. The ocean, if it looked up, would have seen nothing at all. Yet its presence, or even its strong possibility, changes how we read the entire world. A thin shell of observations suddenly sits atop an interior that is no longer simple. In that sense, the most unsettling part of Pluto is not the heart on its surface or the blue ring of its atmosphere. It is the possibility that, deep below the places we have photographed, an ocean has been moving slowly in the dark for billions of years, indifferent to whether anything in the universe will ever confirm that it was there. Pluto was not the last thing New Horizons would see. After rushing past a living world, the spacecraft was steered towards something that had barely lived at all, far beyond Pluto's orbit. In the dim Kuiper Belt, New Horizons met a small body now called Arrokoth. On the first day of January, in the year 2019, the spacecraft flew past it at a distance of about 3,500 kilometers. When the object itself orbited roughly 6.6 billion kilometers from the Sun, it was the most distant close encounter any spacecraft had ever made. And it was aimed not at an active planet, but at a remnant. Arrokoth is modest in every obvious way, end to end. It measures only about 35 kilometers along its longest axis, around 20 kilometers across, and roughly 10 kilometers thick. Its orbit lies in the so-called cold classical Kuiper Belt, near an average distance of about 44 astronomical units from the Sun, taking close to 294 Earth years to complete a single circuit. It is small, remote, and dark. If Pluto strained the limits of our telescopes, Arrokoth sat well beyond them. The shape New Horizons revealed is quietly strange, not a sphere, not a shard, but a contact binary, two lobes, once separate, now joined by a narrow neck. The larger lobe is flattened and elongated, the smaller, more rounded but still slightly squashed. Together, they resemble two unequal bodies that approached one another very slowly and did not shatter on impact, but fused. This is not the violence of late-stage planet building. It is a record of something gentler. Arrokoth rotates with a period of roughly 16 hours, turning once each long Kuiper Belt day. Its spin axis is highly tilted, so that one pole can face the Sun for long stretches of its nearly 3-century orbit, while the other remains in shadow. And then the roles reverse. Over those spans, frost and radiation alternate, but only slightly. The sunlight is far too weak to drive anything like the dramatic seasons we associate with nearer worlds. In color, Arrokoth continues the outer system's preference for red. Its surface is coated in complex organics, including abundant methanol and tholin-like materials, giving it a deep, uniform reddish hue. New Horizons spectra showed clear signs of methanol ice and complex carbon-rich compounds, but little obvious water ice at the surface. Where Pluto displays contrast between bright nitrogen plains and dark equatorial belts, Arrokoth is comparatively monotone, one long, quiet stain of ancient chemistry. The temperatures here push even Pluto's limits further. Estimates suggest that Arrokoth's surface sits around 42 Kelvin on average, with modeled extremes as low as roughly 29 Kelvin and as high as about 60 Kelvin at the warmest sunlit points. At such temperatures, surface processes slow almost to a halt. Ice is rigid, molecules move reluctantly. Whatever shape the body settled into early in its history has been altered only minimally since. The craters tell the same story. Arrokoth's surface is lightly cratered. There are impact scars, but far fewer than one might expect over billions of years. And they are often shallow and subdued. The Kuiper Belt at these distances is a slow place. Relative speeds are low compared to the inner solar system, so collisions tend to be gentle by cosmic standards. When rocks and ice fragments strike, they do so at velocities that are more likely to dent than demolish. Over more than 4.5 billion years, the result is a surface that has accumulated a modest set of marks without being shattered or resurfaced. If Pluto is an essay in change, Arrokoth is a fossil. It orbits in a dynamically quiet zone, with a nearly circular path and low inclination. Numerical simulations suggest that its orbit will remain stable for at least tens of millions of years into the future, and has likely remained undisturbed for timescales of the same order in the past. That stability means it has not been flung inward or outward by giant planets. It has not been heated and remelted, torn apart and recombined. It has mostly continued doing what it started doing, circling. Formation models treat Arrokoth as a window into the earliest stages of planet building. In the dense, cold nebula that once filled this part of space, small icy particles are thought to have clumped together through a process called streaming instability, concentrating into dense filaments that then collapsed under their own gravity. From those clumps, kilometer-scale objects formed quickly. Some merged violently, creating larger bodies that heated and differentiated. Others, in quieter pockets, collided at only a few meters per second, slow enough to stick without pulverizing one another. Arrokoth appears to belong to the second category. The two lobes likely started as separate planetesimals, each assembled from still smaller components. Over time, subtle gravitational interactions and drag from the remaining gas and dust brought them into a mutual binary orbit. That binary then spiraled inward, giving up angular momentum to the surrounding environment, until the pair touched. The impact speed, by the best current estimates, was comparable to a walking pace. The result was a merger without shattering, a double body gently pressed into one. The surface record supports this. On the larger lobe, subtle mounds and units can be mapped, each tens of kilometers across, suggesting that the lobe is itself an aggregate of several primordial pieces. The neck region, brighter and less red than the rest, may consist of finer material that settled or flowed there after the merger. The absence of large fractures or obvious compression features along the joint implies that the two components did not collide at high speed. Compared to Pluto, there is almost no evidence of internal activity. Arrokoth shows no towering mountains like those bordering Sputnik Planitia, no vast smooth plains with convecting polygons, no layered atmosphere casting blue haze. If Pluto is still in negotiation with its own interior heat, Arrokoth has been largely finished with that conversation since very early. Yet the two bodies are linked. New Horizons reached Arrokoth thanks to the same trajectory that took it past Pluto. The spacecraft's detectors and cameras, tuned to read active geology and layered atmospheres, were turned on a world that has barely changed since the era when planets were forming. In a single mission, a small robotic probe moved from a world reworked many times over by internal energy to one that has preserved its initial state. This juxtaposition is more than aesthetic. Pluto and Arrokoth sit at different points along a spectrum of outcomes. Both began as swarms of icy and rocky material in the outer disk. Both were shaped by gravity, collisions, and cooling. But where Pluto grew large enough for its rock to produce long-term internal heat and perhaps to sustain an ocean under its ice, Arrokoth remained small, and its history froze into place quickly. The same processes that gave rise to planets also left behind these untouched fragments. In that sense, Arrokoth is not just a window into the past, it is a control sample. Its nearly pristine condition tells us what the building blocks of outer worlds looked like before they were assembled into larger, more complex bodies. Its contact binary structure shows that at least some of that assembly was gentle, mediated by low velocities and collective collapse rather than by violent, random impacts. It also quietly undermines a comforting notion. We often imagine that time alone will smooth and erase, that given enough billions of years, everything will move toward the same worn state. Arrokoth and Pluto together say otherwise. One small object has kept its original contours for most of the age of the solar system. A larger neighbor, made of similar ingredients, has been reshaped repeatedly, internally and externally, over the same span. Neither path carries a message. Arrokoth does not remember its youth. Pluto does not strive to remain active. They simply follow from different initial masses, orbits, and energy budgets, left to evolve for the same length of time under a distant sun. Our desire to treat one as a relic and the other as a protagonist says more about our taste for narrative than about any hierarchy in their importance. When New Horizons looked back at Arrokoth after closest approach, it saw the outline of the lobes against background stars, confirming their shapes from another angle. That backlit view was not just a technical refinement. It underlined how thin the visible part of this object is. Most of what matters about Arrokoth, the details of its internal structure, the distribution of its mass, the exact path of its formation is hidden, and may remain so. This is where Arrokoth and Pluto meet again. Quietly, one is a nearly untouched fragment. The other, a small world that should have been simple and is not. Both remind us that the categories we build, active and inert, young and old, fossil and living, are temporary scaffolds. We lean on them while the data are scarce. When the data arrive, the scaffolds fall. New Horizons, after leaving Pluto, did not find a grand new planet. It found a lumpy, reddish object only a few dozen kilometers across, circling the sun every few centuries in a path that has hardly changed since the beginning. In that smallness and stability lies its value. Arrokoth is what the outer solar system looks like when almost nothing has happened to it. Pluto is what the outer solar system looks like when almost everything that could happen to such a body has, quietly, over billions of years. Between them, a single spacecraft traced a line from a frozen beginning to a world that refuses to be finished. Pluto and Arrokoth sit in the same distant ring of debris. One has barely changed. The other has changed too much for our categories to stay intact. The region they share was once described as a kind of celestial landfill, the Kuiper Belt, a band of icy bodies that begins just beyond Neptune, around 30 astronomical units from the Sun, and stretches outward to roughly 50 astronomical units. For a long time, it was easier to think of this zone as passive background, a place where leftovers went to cool down and stay there. That picture does not survive Pluto. Pluto is the largest known member of that belt, But it is not unique in its basic ingredients. Its mean density, around 1.75 grams per cubic centimeter, marks it as a mixture of rock and ice, not unlike other sizable bodies beyond Neptune. The Kuiper Belt as a whole likely hosts not just thousands, but more than 100 billion objects larger than 1 kilometer across, most of them made of similar volatile, rich material. Pluto is not a stranger here. It is a representative. When New Horizons showed us mountains of water ice, a convecting nitrogen plain, layered haze, and a probable subsurface ocean, the first instinct was to treat Pluto as an outlier, an exception, a special case shaped by a lucky series of collisions and circumstances that would be hard to repeat. That instinct is understandable. It keeps the rest of the universe simple. If Pluto is unique, then the Kuiper Belt can remain a quiet reservoir, with only one inconvenient world spoiling the symmetry. The trouble is that nothing we have learned about Pluto really points toward uniqueness. Its orbit, locked in a 2-to-3 resonance with Neptune, is shared by an entire population of so-called Plutinos. Its composition, rich in methane, nitrogen, carbon monoxide, and water ice, fits comfortably within the range of outer solar system bodies. Its size is large for the belt, but not unmatched. Scattered farther out are other dwarf planets of comparable or greater mass, including Eris in the scattered disk, along with Haumea, Makemake, Orcus, and Quaoar within the broader trans-Neptunian population. If material, context, and environment are not special, it becomes difficult to argue that outcome must be. In recent years, new instruments have begun to look more closely at some of Pluto's distant cousins. Observations with a large space-based infrared telescope suggest that Eris and Makemake, two of the largest objects beyond Neptune, show signs of internal warmth and possible recent geological activity. Another study reports fluorescent methane gas above Makemake, detected at a distance roughly 45 times farther from the Sun than Earth, hinting that even there, volatiles can still move between surface and space. These worlds are not exact copies of Pluto. Each has its own orbit, tilt, composition, and history. But the emerging pattern is clear enough. Pluto is not the lone restless object in a graveyard of frozen stones. It is one member of a class of bodies that, given enough rock, enough ice, and enough radioactive decay, can harbor internal oceans, active surfaces, or at least atmospheres and ongoing chemistry far out in the dark. The Kuiper Belt itself refuses to stay constrained to the tidy picture we once drew. Surveys, inspired by New Horizons data, hint that the population of small objects may extend well beyond the traditional outer edge of 50 astronomical units, perhaps into a second, more distant ring of material. What we used to call the edge of the solar system is starting to look more like a change in density than a hard boundary. Taken together, these threads point away from comfort. Pluto is not a freak. It is a warning about the way we build rules from partial evidence. For decades, planetary science leaned on a set of gradients. Closer to the Sun, rocky planets, thick atmospheres, vigorous geology. Farther out, gas giants, with their own internal drama. Then a fading of energy into belts and clouds of debris. Somewhere beyond Neptune, complexity was assumed to taper off into background noise. Pluto does not break those gradients entirely. It respects the basics: low sunlight, low temperatures, volatile rich ices. What it breaks is the shortcut that equates low energy with low possibility. A thin trickle of radiogenic heat, spread through a small mixed core, proves enough to sustain an ocean beneath ice tens of kilometers thick, and to drive through a chain of load and stress, the formation of mountains, faults, and cryovolcanic domes. If that can happen in one small body in a belt, that may hold hundreds of thousands of similar-sized objects and more than 100 billion smaller ones. The real question is not why Pluto is active. It is how many other worlds are doing similar things without a spacecraft passing close enough to notice. We are used to treating classifications as if they describe nature. In practice, they describe the limits of our attention. The label dwarf planet was supposed to cleanly separate objects like Pluto from the 8 major planets, on the basis of orbital dynamics and mass. The term Kuiper Belt object was meant to keep a whole population safely in the category of leftover. None of those phrases said anything about internal oceans, nitrogen glaciers, or layered hazes extending hundreds of kilometers above the surface. They were never designed to. The warning Pluto offers is not about nomenclature. It is about what happens when we start to believe that our categories have predictive power they do not actually possess. We told ourselves that beyond a certain distance, under a certain size, with a certain mix of ice and rock, worlds would be simple. Pluto quietly demonstrates that complexity leaks across those boundaries. There is a human pattern hidden in this. Faced with something too large and varied to grasp in detail, we build a map of types: rocky planet, gas giant, icy dwarf, comet, belt, cloud. Each word collapses a vast range of possibilities into a manageable box. For a time, those boxes are useful. They let us organize data, ask questions, design missions. Then something like Pluto happens. A world that checks every box for minor icy body turns out to be reshaping its own surface through slow convection, perhaps carrying a deep ocean, and sustaining a climate cycle that moves nitrogen from pole to pole over seasons that last longer than modern human history. The box still exists, but its contents no longer fit. In that sense, Pluto's behavior is not a comforting exception. It is a reminder that every tidy scheme we impose on the universe is provisional. Somewhere, usually just beyond the reach of current data, reality is busy violating the neat version we have settled on. The Kuiper Belt is particularly good at hiding these violations. It is far, faint, and cold. Most of its members are too small to resolve with present telescopes. Even the largest bodies are often detected as moving points, their spectra thin and noisy. We see enough to guess at surface composition, but not enough to trace mountains or plains. Against that kind of ignorance, the temptation to extrapolate from a few bright examples is strong. Pluto's message is that those extrapolations are less reliable than they feel. If one dwarf planet in that belt can carry layered hazes up to hundreds of kilometers above its surface, run nitrogen glaciers into a convecting basin more than 1,000 kilometers wide, and possibly float a layer of liquid water under tens of kilometers of ice, then we no longer have the luxury of assuming that most of its neighbors are geologically inert. None of this implies that every Kuiper Belt object is secretly complex. Arrokoth shows the opposite path, a small body that has done almost nothing since it formed, quietly preserving its early structure. The warning lies not in a demand that we upgrade every fragment to the status of world, but in the realization that size, distance, and composition are poorer filters for complexity than we thought. We stand at an odd moment in this story. We have a single close look at Pluto and one at a much smaller neighbor. We have spectra and light curves for a few dozen other large trans-Neptunian objects. We have statistical counts suggesting that hundreds of thousands of bodies larger than 100 kilometers and more than 100 billion larger than 1 kilometer inhabit that zone beyond Neptune. From that tiny, biased sample, we are trying to decide how common oceans, atmospheres, and slow internal activity might be. Pluto tells us less about how many such worlds exist than about how cautious we should be in assuming there are few. It undermines the belief that complex, long-lived geology is a privilege of large planets near a star. It suggests that wherever rock and ice are mixed in the right proportions, and wherever even a modest reservoir of heat can be trapped. The universe may quietly assemble worlds that refuse to stay simple. That refusal has consequences for how we talk about habitability as well. An ocean buried under an ice shell, tens of kilometers thick, orbiting at more than 30 astronomical units from the Sun, does not fit easily into diagrams of habitable zones. Yet, from the perspective of chemistry, such an environment can persist for billions of years, far longer than many surface oceans closer in. If Pluto can host such a sea, then the outer solar system, and by extension, the outer regions of other planetary systems, may be littered with similar hidden reservoirs. Again, Pluto issues no invitation. It does not ask to be included in our catalogues of potentially habitable worlds. It simply exists in a state that makes those catalogues look incomplete. The temptation, after all this, is to try to fold Pluto back into a new, improved set of categories, to say that we now recognize a broader class of oceanic dwarf planets or active Kuiper Belt worlds, and to reassure ourselves that with a few new terms, the universe is once again under control. The warning is that this cycle has no natural endpoint. New data will always be waiting to show where the current version of our order breaks. Pluto is not an exception that we can set aside once explained. It is a reminder that nature does not read our definitions before deciding what to do with ice, rock, and time. We are the ones who need definitions. Pluto just keeps orbiting. It does not know it was once called a planet and then something less. It does not know that we argued over its name, or that we sent a machine across the dark to stare for a few hours and then leave forever. It is not flattered by attention, and it is not wounded by neglect. It turns, slowly, under a faint sun, reshaping itself in ways that would have gone on exactly the same if no one had ever looked. We are the disturbance here. For most of our history, the night sky was a backdrop, a place to project myths, then geometry, then physics. We learned to draw clean lines: planet, moon, asteroid, comet, dwarf planet, debris. The lines felt solid. They told us where importance stopped. They told us where we could safely say, beyond this, nothing much happens. It's a reader describes to bees. Pluto sits exactly where those lines were supposed to protect us, and does not obey them. It is small, so it should be simple. It is distant, so it should be finished. It is cold, so it should be still. Instead, under a sky that barely brightens, it moves nitrogen like weather, carries mountains of water ice, possibly hides an ocean, and records a climate that unfolds on timescales longer than anything we build civilizations around. Nothing about that is dramatic in the way we usually mean. There is no spectacle designed for us, just a quiet refusal to match what we find convenient to believe. Standing on a world like ours, with our brief lives and urgent meanings, it is tempting to ask what Pluto teaches. But teaching implies intention. There is none here. Pluto does not care if we understand it. It does not care if we ever return. It is not a symbol of resilience, or of being misunderstood, or of any other story we might find comforting. What it offers instead is something harder to hold: the realization that reality is perfectly willing to be more complex than we are ready for. In places we have already decided are empty, Pluto is a silent world that, by our logic, should not exist as it is. It exists anyway at the edge of our system, at the edge of our categories, continuing to change in the dark, whether we are looking or not.